Welcome to my channel. In this video, we are going to be solving problem under damped oscillation. So the problem we are going to be solving is given in the form of a statement. The equation for a damped harmonic oscillation is given as this expression. So we're asked to calculate A, the angular frequency of the oscillation, B, the natural angular frequency, C, the initial energy per unit mass of the damped oscillation, then D, what is the nature of the oscillation? So to solve this particular problem, we recall the standard equation of this form, the general equation, which is given as this, right? So we can compare letter for letter this equation to this equation, and just by observation, we can see that our C naught is just 10. Our W prime is just pi over 2, right? Then half of W squared is 0.125. So if we find just W squared, just take 2 here, it becomes W squared is equal to 0.25. Now our W prime here is the angular frequency of the oscillation. So when we compare, we can see that pi over 2 is just the expression. So we can represent it in radian per second, and we have W prime equal to 1.57 rad per second. So we just say 22 over 7 divided by 2. That gives us this value, and that's in rad per second. That's it. So we'll move on to the natural angular frequency. So we recall this expression, right? This equation can be found in our previous video, how we got this equation, titled damped oscillation. So you can check our previous video on damped oscillation. Everything that has to do with damped oscillation, equations governing damped oscillation, you'll find it there. So we have found this one to be the angular frequency. This W naught is the natural angular frequency. But we know this one, we just found this. We know this expression, we can determine this. So we already know our C naught equal to this, W prime is this one is this, W squared is this, W prime is given in this form. So if we make this one the subject formula by squaring both sides, this one becomes W prime squared. You take this one to this side, becomes W prime squared minus this, making this one. So we have something of this form. So this is our natural angular frequency. We already know this, we know this. We can pick our values from here and slot them here. And from here, we can say this one is the same thing as this. We already know this, half of omega squared is 0.125. Then we square it. This one is already this. And that gives us our value here, which is 1.57 rad per second. So this is a natural angular frequency. Okay, so the next is the initial energy per unit mass of the damped oscillation. Now, for this particular one, it's important for us to generate the expression for the energy. So we start with the expression for the energy, which is as a result of the potential energy of the spring plus the kinetic energy of the spring at any point in time. So let's concentrate on our potential energy first. So this potential energy is the expression as half of kx squared plus half of mv squared. We already know our x squared, which is given in our previous slide. We'll just square it and fix it. So for the potential energy, we have half of k, c naught this all squared. This is our x. Our k here, remember, can be gotten from this point, which is W naught squared is equal to k all over m. W naught squared, natural angular frequency, is W naught squared equal to k all over m. So our k, if we make k the subject formula, it becomes m W naught squared. So it can be replaced by this k. Now, this one is when the system is displaced from the equilibrium position. But when it is displaced a little bit beyond the equilibrium position, then we have this expression, which is PE equal to this. So the difference between this is just the cos squared here and the sine squared here, right? So at this point, we'll concentrate on this one when it is displayed a little bit from the equilibrium position. So these are potential energy. Then we'll go to our kinetic energy, which is half of m. X dot means v, because the x dot here means differentiation of x with respect to time. So we have x dot squared equal to half of m. If we differentiate our x with respect to squared, we have this, although it's a little bit lengthy, so I just shortened it here so that it won't take much of our time. So we can always check how this one was derived. So we have this expression. So at the end, our energy, so recall that this expression, W prime equal to this, and we have if W naught is far, far greater, that's this one is far, far greater than this, then we have W naught must be equal to this, so which is this one. And what that means is that if this one is far, far greater than this, then this one will be insignificant. Then square root of W, the natural angular frequency squared, will be W squared. So W prime will be equal to this. So at the end, our W prime here becomes W naught at this point. So if you fix kinetic energy and potential energy into the total energy, we'll have this expression. So this is the potential energy part. This is the kinetic energy part. So we can see here m, this one has changed to omega naught squared, right? Still retaining cos squared theta. Then our k here, we know, remember that here, this part was k, and we said our k is mw naught squared, if you remember. So we can factorize the common expression, and we have this one and this. So at this point, everything here becomes 1. So we have this expression. So this is the total energy at any point in time. But we're asked to find the initial energy per mass. So if for us to find the initial energy, we'll just put 0 here. Wherever we see t, we'll put 0. Then we'll take our m down, put 0 here, everything goes off. So we have initial energy per mass equal to half of omega, that's omega naught squared, c naught squared. Everything, if you put 0 here, exponential 0 will become 1. So we have this. But now we already have our W naught to be this and C naught to be this. So if we fix them in, we have energy, the initial energy per mass to be 123.2 joules per kilogram. Okay, so finally we look at the nature of the oscillation. Now, for us to know what kind of oscillation we are dealing with here, whether it is underdamped or lightly damped, heavily damped, that's overdamped, or critically damped. So we need to check this expression. And that's the fact that since we have W naught far, far greater than these parts, so we've seen it, that this one, W naught, if we square it and we solve for this one is far, far greater than this. You can check the calculation with those expressions that we've given. Then we'll notice that this one is greater than this. And if this is greater than this, that means this part is positive. And if that's the case, then the oscillation is slightly damped. And that's it. I hope you enjoyed this lecture. Please like, share, and follow for more. Thank you.